Hi, everyone. So indeed, this is a collaboration with my PhD student, his co-supervisor, and my colleagues in University Autonomous of Madrid. Juan de Lara is also here if you have more questions. So to give you a very brief introduction here, so domain-specific language engineering, when we build domain-specific languages, typically we build a meta model, we build some concrete syntax, and then we can generate a domain-specific editor from it, where we can build these domain-specific models using the concrete syntax. In this talk, we're focusing only on graphical concrete syntax, but the tools we use, we're not dependent on the tools we use. So here, this is just modeling with EMF, and this is concrete syntax with Sirius from Arduino Designer, but we're not bound to these. Very often, also, the DSL will have some kind of semantical rules that can apply there. For example, operational semantic rules. So in our case, we're using I'm going to use the running example of the Pac-Man game configuration DSL, where we have a game that has a scoreboard that has a series of tiles of grid nodes that are placed on the canvas, and then we have Pac-Man, Ghost, and Food that can be placed on them as an initial configuration of the game. And this rule here shows that if I have a Pac-Man on a node and the food on the same node, then the food is deleted, so it's basically and the score is updated so that he's eating food, right? And the concrete syntax we're using is this. Now, very often from these models, we serialize them so that they're stored using, well, at least in the Eclipse world, they use XMI, so this is the actual representation of this model, the way the file is actually saved. Now, when we come to version control systems in an editor, very often, in version control systems, comparison is differencing is a very crucial operator. And to apply these on models, well, so if we go naively, if we use like Subversion or Git, then they use the diff algorithm that is really text-based, where we look at the differences between lines. So if I just show you this is basically committing a model on GitHub and then committing another version of the model on GitHub and asking it to do the diffs. And that's what we get. Of course, this is by no means domain-specific user-friendly. It's very hard to know what has happened. In fact, here we see that the value has changed for the scoreboard, and then the Pac-Man, something got lost, an ID was changed. It's not very clear what happened. But of course, if I show it to you in concrete syntax, you actually see what happened, right? The Pac-Man was here, the food was here, the food is gone, the Pac-Man is here, the score has changed. So you can imagine what happened, right? So, of course, if the line changes in XMI will lead to false positives, where we detect differences that are not very meaningful, and you have to manually find the semantics of the changes. What do they mean here? That the Pac-Man has moved and then ate the food. So to overcome these limitations, there are some model-based tools approaches that exist here, and basically what they do is they look at the abstract syntax of the model and they find structural differences. Typically, they are based on identities, so every element has an ID. As you can see here, every element has an ID. They also look at the difference between attribute values and the references, how they're pointing. So here, I actually, the models that we have here, we've applied them with EMF compare, which is such a tool. And what you see here is a difference model that represents all the changes. You see here the scoreboard value changed, and there's a food that was added somehow, and a grid node that was something changed, right? The on has changed. And here we see the juxtaposition of the model version 1 and version 2, and it's not very clear what the difference is. So there's a comprehension gap for the user of, what does it mean? What does this diff model mean? It's not semantically meaningful for the user. And also, everything is in purely concrete syntax. So basically, what we're seeing here is a tree view of the XMI in the end. Okay. So this is, again, not domain-specific, user-friendly. So what we propose, what we would like to have, ideally, is to say, well, given these two models, I would like to compute the difference and show me the difference in the same representation as the two models. So here, saying that that link has been deleted, that link has been deleted, that link has been created, and that value has changed. So at least here, we can understand more in a more domain-specific way what actually happened. But maybe this is actually even better. So we can go one step further and give more semantic meaning by just saying, I don't want to know exactly what has been deleted, what has been created. I just want to know semantically what happened. So I just want to report that the Pac-Man has moved to the right, and the Pac-Man ate the food, and that the score value has changed. That's the only thing I need to know from a domain-specific point of view. And so that's what we try to do. So that's the DSM compare approach that we propose here. So we have two roles, the DSL, the language engineer, and then the user, the domain expert. So the DSL engineer has to, of course, provide his language with the abstract and concrete syntax. And what we do is that we generate a difference environment, a difference editor, so that the difference model can be represented in a somehow DSL that is the result of a transformation from the original meta model and the concrete syntax. And then to specify the rules, what semantical rules can be applied, well, we also provide an environment for an editor to define the rules using concrete syntax derived again from the DSL. And then the language engineer can define domain-specific difference rules. Now, please note that that is not necessarily the operational semantical rules. They are difference rules, and we will see the difference between them in a few minutes. Now, from the user point of view, the DSL user point of view, well, of course, he builds his models, he commits his models in the version control system, and then he wants to see the difference between them. So we apply the difference algorithm, and then it reports the domain-specific difference model, so the differences in the form of a diff model with all the fine granular differences, so that actually conforms to that diff meta model, right, to that diff language. And then what we do is we apply the domain-specific diff rules on that diff model so that we actually get semantically meaningful differences. So in the rest of the presentation, I will focus on these two transformations, on how to derive the domain-specific difference meta model and then the environment to create these rules. So let's start with the first one. So if this is my original DSL, this is what the difference meta model will look like. That is completely generated automatically. We have a transformation. The algorithm is in the paper. So what are the main steps of the algorithm? Well, the first thing we do is that we copy the meta model, the original meta model. Why do we copy the original meta model? Because we want to reuse as much as possible the elements that are there and as well as the tools that are around it. For example, the concrete syntax, right? So we're going to get to that in the next slide. So more specifically, what happens is that for every class, let's say score here, okay, for every class in my original meta model, I will create a subclass called diff that class, and I will add a diff kind, which can be an enumeration of the class has been added, deleted, or modified. And then for every attribute, we're going to add a new attribute, right, and, with the same type that will, if it's modified, then it will have the new value here. And so you see here, we reuse the same class. So everything that the original class had, the associations, the attributes, everything, the constraints, everything will be inherited by the subclass so that it stays in the same domain. And then for associations, so for example, this on association, it's here. So what happens, so of course it's copied, but then what we do is we create a class that corresponds, that represents that on if it's added or deleted, right? That association if it's added or deleted. And what we do is that we multiply by 2 the maximum cardinality. So here the maximal cardinality is 1. It's the right part of the 1. And we multiply it by 2. The reason why we multiply it by 2 is that for every association, it can be added or deleted. And we need to be able to represent this in the diff model, that it may have been added, it may have been deleted on the instance level. So that's why we actually multiply it by 2. And so we do that for the whole, all the classes, associations. The inheritance links, they stay there, so the inheritance hierarchy stays there. Okay, so given that, what we can do is, for the advantage of the reuse here of the original DSL is that if I had my concrete syntax defined for that original DSL, well, what I can do is reuse it exactly. And so by reusing it, everything, so if this had, let's say, a square as a concrete syntax, well, in this meta model, this will have a square also, right? But it's also inherited by this. So this one will also have a square. However, for this one, I probably want to say that, well, maybe I'll change the concrete syntax for when it's added, deleted, modified. And so that's exactly what we do here for every element that we have, for every concrete syntax that we have here. We generate a default icon. Basically, we put an X, a plus, or a tilde for the corresponding difference operation. And so we do that for all the classes and the associations. Okay, so that's also automated completely. Of course, because it's icon-based in this case, the user can customize the icons if he wants for the difference part. Okay, so given this first transformation, what we have is, given 2 models, we apply a model-based comparison. So in our case, we reused EMF compare so that we get a diff model. And then from that diff model of the abstract syntax, we simply do a transformation. So that can be done, that is a very simple transformation, it can be implemented in ATL or something like that. And to produce basically a model that is an instance of the diff meta model we just created using the concrete syntax. So up to now, basically what we've done is we've taken a model-based comparison tool and allowed it to represent the differences in concrete syntax. So now let's go to the next step, which is adding the semantical differences. So for that, we need the DSL engineer has to be able to define his own rules, his own difference rules. So what we do is we take the diff meta model, the one we just created, and we copy it again for the rule meta model. And we rename all the classes, we prefix them by pattern, because basically what we're doing here, it's a rule, so it's going to have a pattern that has to be matched on the diff model. So for every class, we add an ID of the pattern. We will see why this is useful in the next slide. And we make sure that and the root element, so we have to find the root class, here it's game, that contains all the other elements transitively. And we will create a new root, which is the rule, with a name and a set of constraints that can just be written, in our case, in pure Java syntax. And so we also, for every class, we also add an attribute called filter, which when set to true, will hide the object, basically. Okay, the difference object. So we do the same for the concrete syntax. We also produce the concrete syntax for the rule definition environment. And from there, we can generate automatically an environment to define the semantical rules. So here, if we look at the semantical rules, what we have is, so this is the name of the rule, so Pac-Man eats food. And what does it say here? It says that if I have a grid node with a Pac-Man on it and a diff, so a regular Pac-Man from the original DSL, a diff food with his diff kind deleted. Then and the scoreboard value has changed such that there's a constraint that says that its value is less than its new value. Okay, so the scoreboard, this is a diff scoreboard with a value less than its new value. Then what will happen is we will create this Pac-Man food object, okay, and we will filter that association here of the food being on the grid node. Okay, so it's very, very similar to a graph transformation, right? Left-hand side, right-hand side rule. Okay, so from that, what do? We take the diff model we produced before, and we apply all the semantical diff rules that have been defined, and we apply them on the diff model to get the final more semantically meaningful difference model. Now, one question can be, where do these semantic diff rules come from? Because all the magic comes from there. So it turns out that for DSLs that have operational semantics, well, that's probably where you're going to get the difference model. So for example, for the Pac-Man game, you have the rules for dying, for moving, for eating, for moving the Pac-Man, things like that. So that's where you can get inspired from. Currently, the rules have to be developed manually, but this is some research we're looking into, is can we try to infer the difference rules from operational semantic rules if they are provided by the language. Another possibility to find the difference rules are from maybe refactoring rules. So for example, if your DSL, if your domain is, let's say, feature models or class diagrams, then they don't have a operational semantics, right? They don't execute. They just are. So one of the meaning we can give is some refactoring rules. So for example, pull up, remove dead features, migration, etc., etc. In general, these rules will come from what we call the pragmatics of the DSL. This is how the DSL is actually used, and basically you need to sit with the domain experts to find out what the meaningful operations mean. Okay, so that's the approach, and so we've done some validation. There's a lot of validation that can be done for such a project. For the conference paper, we chose the following three. So we basically tried to find if it makes sense to do what we did. Okay. So is it possible to extract semantical diffs from fine granular diffs? Is it something that we can do? Are final granular diffs more verbose than semantic diffs? And are the semantic diffs something that can recur multiple times? So it's not something that you find only for the difference between these two models, but it's something between, more models. If I have 10 versions of a model, well, I might find that semantic diffs between more than two models. So for that, what we did is we looked at a third-party DSL that is called Arduino Designer from GitHub. So we had to find one which had a commit history that was publicly available, and from a tooling point of view that used the same technology that we did, so that it's easier to map to DSM compared to our implementation. So with Sirius. And so it turns out that Obeo has done Arduino Designer, which is an open source electronics DSL for Arduino. It's actually not trivial. It's actually quite complex because the model itself is segregated in two parts, which is the hardware part. Okay, what is the configuration of which device is connected to which pin, and then what they call the sketch part, which is the actual program, that the C code that will be generated from. So it's kind of a workflow, control flow thing. And so what we did is we retrieved the commit history of the different models, and we looked at the commit messages that were used by the committer to give us a hint of what was the meaning behind that change. And so that's how we derive the semantical rules. So to answer the first question, is it possible to find, can we extract semantical diffs from fine granular diffs? So the first thing we see is that the only difference mechanism we had was the one provided by Git. So of course, having this versus having the version with DSM compare, where we represent the hardware and the sketch with the difference elements, was probably more useful for the users. And you see here, this is a refactor while loop that happened twice. So that's for research question 1. For research question 2, we looked at all the projects and basically reported the fine granular diffs of the number of classes and association reported by EMF compare. So for this fade light project, the version 1 had a while, the while loop for the fade light example used 20 classes and 22 associations. And then when we apply the refactor a while loop semantical diffs, we end up with only 1 class and 2 associations. So it simplifies a lot the diff model to understand that. And then the last one was how many, is it possible to find multiple times the same semantical diffs? And so we found that there are more than 1 occurrence for some of them, but not all. Okay, so our future work is to increase the expressiveness of the rules. So for example, one possibility is to increase it with the negative application conditions. So it's not only find something, so find that this structure in the diff model is present, but we want to say maybe this structure is present and that is not present. So that makes it a bit more expressive. We can express more things with the full power of first order logic. And we also want to investigate what happens if I have multiple rules that can apply in the same place of the diff model. And so how do you choose which one? Okay, so that's something we're working on also currently. Of course, what needs to be done is a user study to evaluate the usefulness of DSM compare by saying, well, this is if I give you, model-based comparison or Git-based comparison, and this is if I give you DSM compare, and then I ask that to domain-specific experts, and we will see if it's more productive for them to use one or the other. And our ultimate goal is to integrate this comparison approach, this domain-specific comparison approach in model-based version control systems. So that's it for the presentation. So if you have questions, please go ahead.
Any questions?
So I'm assuming the two models you're comparing may conform to the same meta model.
Yes.
So what happens if you wanted to compare something from the past where the meta model has evolved? Can you still like just put a hole there where a concept is missing, or is that something that you can do now, or that's something that can be extended?
Yeah. So that's a good question. So we assume, one of our assumptions is that the meta model is the same because we assume that the language has not evolved and it's the user who are actually using it. It's less likely that the language evolves than the model, so that was our assumption. But indeed, if the meta model evolves, then we will need to find a way to also evolve the diff meta models to be able to conform to that. Yeah. And so what's interesting there is that you may think also of like higher order differencing, where you would define semantical rules to find the difference between the meta models and then apply them to the models. So that could be one way of solving that. Yeah. Yeah.
What kind of properties would you expect model DCS?
Yeah, that is a good question. I just wrote a project proposal on that. It's a lot of features. We actually have a paper that gives a feature model of the version control for model-based. One thing is comparison done at the domain-specific level. one thing, the merge has to be done also at the domain-specific levels. These are the two main operators. Also trying to redefine what does it mean to commit, to push, to pull, to update in domain-specific terms. To look at not only linear versioning or tree branching versioning, but maybe some other kind of structures that make sense for the domain. So there's plenty of things that haven't been touched yet in the world of version controls for models, for domain-specific models.